Welcome back. This is Mr. Hassan's Maths channel. I'm now going to answer question number 6 from the January 2014 International A-Level Edexcel. This is a Mechanics M1 paper from the old specification, but of course this is very relevant to the syllabus now. So here we have a question about connected particles, inclined planes, dynamics, friction, a lot of different things involved here. So we have two particles, P and Q. They have masses 0.1 kg and 0.5 kg respectively, P and Q, 0.1, 0.5. The particles are attached to the ends of a light inextensible string. Attached to the ends of a light inextensible string. Particle P is held at rest on a rough horizontal plane or table. The string lies along the table and passes over a small smooth pulley which is fixed to the edge of the table. Particle Q is at rest on a smooth plane which is inclined at an angle or inclined to the horizontal at an angle theta, where the tangent of theta is 4/3. The string lies in the vertical plane which contains the pulley and a line of greatest slope of the inclined plane as shown in figure 2. Particle P is released from rest with the string taut. During the first 0.5 seconds of the motion, P does not reach the pulley and Q moves 0.75 meters down the plane. Find the tension in the string during the first 0.5 seconds of the motion. Okay, so I'm going to first look at some of these terms and explain what they mean. So it's a light string, which means all the way through the string the tension is going to be the same and we don't consider its mass. It's an inextensible string, which means all the particles attached to the string, as long as it's taut, will have the same acceleration. When the string is taut, this is another word that we have to explain. All right. Where is it going to mention here? The string taut. Okay, the string is taut. That means there's tension in the string. So when the string is taut, the acceleration of both particles will be exactly the same. They'll move with the same acceleration, the same magnitude of acceleration, then they'll move with the same speed, and they'll move exactly the same distance as each other, these two particles, as long as they are attached to the same string. Okay, and what else do we know? It says here, particle P is held at rest on a rough horizontal plane. Okay, so on the horizontal table, we're going to have friction. There's going to be some friction now involved in this question. Right, the string lies along the table and passes over a small, smooth pulley. A smooth pulley means there's no friction in the pulley and the tension in the string on either side of it will be the same. Sometimes they do ask, especially in the Edexcel questions, about how we use some of our modeling assumptions in answering the question. Okay, how did we use them? So we should understand all of these points very, very carefully. So a smooth pulley means that the tension on the string on both sides will be the same, which is fixed to the edge of the table. Particle Q is at rest on a smooth plane, so no friction on this plane, which is inclined to the horizontal at an angle theta, where tan theta equals 4/3. Okay, so tan theta equals 4/3. Now, this is also important because we need to know, basically, when we resolve forces, especially for Q, we need to know what sine theta is and we need to know what cosine theta is. And we can work out what those are in the exact form by using this ratio that they gave us, which we'll deal with when we get to it. Then it says the string lies in the vertical plane which contains the pulley and a line of greatest slope. Now, a lot of students don't understand what this means, the line of greatest slope of the inclined plane. Basically, what it means is if you're looking at the slope, supposing we're looking at this from an angle like over here. This is our eye, we're looking at the slope. So if we look at it at a bit of an angle, we'll see something like this. It will be a slope going up. So there's a pulley, there's a particle Q, and this is the string. So it's basically, it's the shortest distance between these. It's not like at an angle here. It's like in the same vertical plane. You know, this basically the line of greatest slope okay, of the plane. Okay, that's what it means. It doesn't really affect the question so much, but some students, they don't understand what some of these terms mean and they have a bit of an issue with that. Okay, then it says particle P is released from rest with the string taut during the first 0.5 seconds of the motion. P does not reach the pulley and Q moves 0.75 meters down the plane. Okay, so we've got to consider a few things here. We want to find the tension in the string during the first 0.5 seconds of the motion. So let's take this diagram. I'm going to draw the forces down here because I don't have to keep scrolling up and down every time I'm going to do my calculations. So what do we know? We know the mass of both particles. So we can draw the force that's acting on them due to their weight. So P has a mass, as they told us, of 0.1 and Q 0.5. So therefore the weight is 0.1 G newtons and 0.5 G newtons. Okay, you also have the tension in the string. You have the tension in the string here and here. Okay, so that's another force. Let me draw it properly. Tension. Okay, so you have the tension in the string. Okay, it says P is on a rough table. Okay, so for P, of course, for both of these as well, you'd have your reaction force acting perpendicular to the surface. So here will be vertical, here will be at an angle. And here you're going to have a frictional force acting, which is going to oppose the motion. And that's going to be F max as the object is moving. So that's the reaction force for P. That's the reaction force for Q. Okay. And that's basically here we have a smooth plane, so we don't have friction acting. Okay. So that's the situation that we have right now. Now, what I can do here, we want to find the tension in the string during the first 0.5 seconds of the motion. Now, we know a few bits of information. We know that both objects, not just this object, but it says during the first 0.5 seconds of the motion, okay, P does not reach the pulley and Q moves 0.75 meters down the plane. So if this moves 0.575 meters down the plane, okay, this also moves 0.75 meters along the table because they're attached with a light and insensible string. So the distance that this moves and the distance that moves will be exactly the same distance. So this has moved 0.75 meters, and so is this. Now, if we want to find the tension in the string, okay, what we can do here, we need to consider the one or the part of this which will give us the answer in the easiest way. Okay, so if we think about this moving 0.75 meters down the plane here, that distance, in the time of 0.5 seconds, okay, we can use this here to find the tension. The problem with this one is we need to know the frictional force first, because the resultant force here is going to be T minus Fm. But here the resultant force is going to be the component of the weight down the plane minus the tension, and that's going to be the mass times acceleration. So with this, I don't need to know about the coefficient of friction. I can just deal with the weight component and the tension. This is a smooth plane, there's no friction here. So I can get an expression here which will involve just the tension without the frictional force. And I can work out the acceleration of the system. Why? Because we have been given some information. If we think about the Suvat equations, we can work out the acceleration because we know this object has moved 0.75 meters. And I could use either of these two to find the acceleration. It would be the same for both. We know they both started from rest. We don't know what velocity they've reached. We know the acceleration that we can find, and we know that this happened in 0.5 seconds. Right? So we can use Suvat. We have S, we have U. We have T, we need to find A. We can use the formula S equals UT plus a half AT squared. So we know S is 0.75. We know U is 0. We know T is 0.5. We know A is what we're trying to find, and this is 0.5 squared. So we're left with 0.75 is equal to, this becomes 0. That's a half times A times 0.5 squared. So it's going to be a half of a quarter, a half of 0.25, so it's 0.125. In fact, I'll do, I think it's easier to do in fractions. I can just use my calculator actually, but we can use this in fractions, it'll be easier. This is 3/4 equals, and that's a half times a quarter, which is 1/8. Half times, because a half squared, 0.5 squared is a quarter, a half times a quarter is 1/8, so that's going to be A here. That cancels with this, you're left with 2. 2 times 3 is 6. So the acceleration is 6 meters per second squared. So that's the acceleration of the system. Okay, so now I can consider Q. So this is considering either of them. We'll get the same answer, of course. So now if we consider Q, if we just look at the particle Q, we will be able to figure out what we need, because if we consider Q, we can resolve the forces acting. Now, I know that this angle here is theta. Right? I know this angle here is theta. How do I know it's theta? Because the angle to which the plane is inclined is always equal to the angle between the weight and the line perpendicular to the plane. Okay, that's always the case, and it's due to similarity, as I've shown in many of my previous videos. Okay, so basically, if you consider, sorry, this angle is theta here, not that angle. It's my bad. Yeah, this angle here is theta over here. The angle between the weight and the plane. So that's angle theta as well. This is theta, this angle over here. All right? And we can understand that from these two triangles that are formed. This big triangle and this triangle over here. Okay? Give me a second. This angle here is theta. Okay, so we can see here that if we want to resolve this force down the plane, okay, we can do that. Change the color, make it a bit thinner. If we resolve this force going down the plane, this direction, we're going to get 0.5 g times, going away from the angle, sine theta. 0.5 g times sine of theta. Okay, so that's the force going down the plane, and up the plane is t. So we can resolve the forces taking down the plane as positive as it's moving down the plane, and we can say 0.5 g times sine theta minus the tension is equal to the mass, which is 0.5 times A. Okay, so we have 0.5 g times now sine theta. What is sine theta? Well, we know that tan theta is 4/3. So if we think about a right angle triangle, okay, say this is theta, say this is 4, this is 3. This is going to be 5 by Pythagoras. So tan theta is 4/3, opposite over adjacent. So sine theta is 4/5. And cosine theta is 3/5. So we're interested in sine theta, which is 4/5. So that's going to be 0.5 times g times 4/5 minus t is equal to 0.5 times 6, because we know the acceleration is 6. So the tension, therefore, is going to be all of this minus that. So I can just put that in my calculator from the beginning now. Let's have a look. So we have 0.5 times 9.8 times 4/5, and we're going to take away 0.5 times 6, 0.5 times 6. That gives you 23/25, which is 0.92 newtons. So there's your answer to part A of this question. And now we're going to move on to part B. All right, so part B tells us to find the coefficient of friction between P and the table. So this is the table, this is P. We know that there's friction. We know the tension in the string is going to be 0.92 newtons. We know the acceleration is 6 meters per second squared. That's the information that we know from the previous part of the question. So what we can do here is we can try to work out what the frictional force is acting. Here, we know that F max is equal to mu r. And we know F max has been achieved because the object is moving. F max being the maximum amount that friction can be produced in the situation. Okay, it's moving, so we have it achieved, basically F max. So we want to find the coefficient of friction. So we need to find what R is, and we need to find what F max is. Now R is pretty simple. We can see R is going to be 0.1 G. That's fine. Okay, there's no other forces acting like at an angle, all horizontal and vertical. So the reaction force at P is going to be 0.1 G. That's fine. We got this part. Now we've got to find what F max is. So we can resolve the forces acting on P, okay, horizontally, in the direction that we're moving in. So we know that we got the tension minus F max, so 0.92 minus F max, which is mu times R. Okay, in fact, I'll just call it F max. Minus F max is equal to the mass times the acceleration. So it's 0.1 G times acceleration. So not G, sorry, 0.1. Don't make that mistake. We don't put the G there for the mass. Okay, G is the force, it's the weight. We want the mass. So it's just 0.1 times the acceleration, which is 6. So we can say that F max is going to be equal to 0.92 minus 0.6, which is going to be 0.92 minus 0.6, which gives us 8/25, which is 0.32. 0.32, okay, that's F max. So now we can find the value of mu. Okay, we can say that, F max equals mu times R. Therefore, mu is equal to F max over R. So we have 0.32 divided by, and we have 0.1 G. Okay, so we have 0.32 over, so we have the answer over 0.1 times 9.8. That gives you 16/49, which I'll write to 3SF. So mu is equal to, you're going to have 0.32653, 0.32653. So we can say mu is equal to 0.327, 3SF. Okay, so there we have the answer. Let's write that 7 a bit clearer. 0.327. That is the coefficient of friction between P and the table. Okay, so this is a question that was requested by somebody on the channel for me to answer. I hope that was clear. Other questions from this particular paper can be found in the playlist that will appear in the top right of the screen at the end of this video. Other questions from this topic which is, dynamics, connected particles, and friction, forces of friction. I'll make 3 different playlists for that. You'll find in the playlist that will appear at the end of this video. Thank you for watching and see you soon.